So like I said, if you want to go back and look at that, that's a really good video that not only explains the operation of a diode, it also gives us a really good operation of a transistor. I did notice that they didn't have any resistors in the diode circuit, which should have caused some problems. But they did have them in the transistor circuit. So these are two symbols. These are normally what we represent it. Of course, this guy here is going to be really thin and lightly dosed. This is a symbol. This is a not pointing in, not pointing in. This is pointing in, so this is a PNP. A small base current can control a proportionally larger collector. Kirchhoff's current law says that the total current entering a junction must be equal to the total current leaving that junction. Therefore, the sum of the collector current and base current will equal to the emitter current. So you notice on the video, of course, I put a resistor right there. We had a battery, so we'll look at the NPN, and we 5-volt battery. So its current flow comes up here, goes up through the emitter. I'm just going to draw it over. In fact, let's do it in a different color. Then I'll come over here and I have a collector resistor. And that is an NP. So what we have is, this is what I want to make sure you understand, is current flows out here, up through the emitter, back through the base resistor, back to this power supply. Current flows here, up through here, back through there, back to this power supply. So notice I have two arrows or two paths that go through the emitter. So the base current and the collector current flow through the emitter. So that means IE, so E is the emitter, is going to equal to IB plus IC. So the emitter current is always the largest current in the transistor if it's operating correctly. And then of course we can transpose that to come up with that. The sum, so here's our formula. So IE is equal to IB plus IC. IE is the largest current in the BJT. Of course, you know that's going to be on the test. So IC would be equal to IE minus IB. So IC is the second largest current flow in the BJT. So IB would be equal to IE minus IC. IB is the smallest current in the BJT. Since IB is so small, for calculations, what we're going to do is we're going to say that IC is approximately equal to IE. And it's going to be very, 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 very close. There is a simulation software package that costs a lot of money. It's called Multisim. They have a free version available on the Multisim website, which y'all can sign up for. You'll get an email from them every once in a while, but it's not as monotonous as some places that I've signed up so far. So we'll go up there and look, and you can save your circuits. It's really, really, really neat. So this is one of the circuits that I saved, and this is showing us basically the same thing. So wait till it finishes loading. So this is 2 battery bias, and like I said later on, we'll come back and look at biasing with one DC voltage source. So I have a 15-volt battery here. I have a 15-volt DC voltage source here. I have a 5-volt DC voltage source here. I'm using a 1K ohm resistor in my base circuit, and I'm using, I can't see it. I think it's a 10K up here in my collector circuit, but I can't see it. I have my simulation set up for interactive, and what I can do is I can start the simulation. And then what we can do is we can come up here, we can change the base current by changing the percentage on this. And hopefully it works. So you can see I'm going to start dropping my percentage down. And so right here, guys, this is the measure of my base current. So right now I'm putting in 226.8 microamps of base current, and I'm getting 15.09 milliamps of current in my collector, and I'm getting in my emitter, that was a big mistake, 14.86. Now if I add this and this together, we should come up and get this. But notice the highest base current, the highest current is in the emitter. So we'll keep increasing the percentage. And notice my base current goes up proportionally. Now what you're looking is, if the current goes up, this resistor right here is going to drop more voltage, which means there's going to be less voltage dropped across the transistor. So notice as I do this, I have 4.25 volts on my collector. According to Kirchhoff's law, I would have about 11 volts on my, up here on the top of the resistor. So I'm going to get to the point so now I have 15 volts dropped across my transistor. So that means the transistor is totally cut off. Now when we go the other way, now look, now we've only got, 117 millivolts across the transistor. So now the collector resistor has to be dropping pretty close to 15 volts. But what I want you to do is we could calculate the gain of this thing, current gain. So this is a current valve. It's not a voltage valve, it's a current valve. What we're doing is we're controlling the amount of current. But what we can do is we can use a resistor in series with it, and it appears like we're getting a voltage across the transistor. Are we okay? So this is a real neat simulation software package that's available to you. So now the transistor is dropping all the voltage. And when I swing it over on this side right here, the transistor is almost dropping 0 volts. So 45 millivolts across the transistor. So there's basically 15 volts across the resistor. You'll see that? Well, what I want you to do is we look at this thing, if we're looking at current gain, then what we'll do is the current gain is based on the collector current compared to the base current. So that means I would take 10.4 something milliamps, and I would divide it by 104 point something microamps, and we'll see this transistor has a gain of right around 100. I can just about do that in my head. So that means my collector current is going to be almost 100 times the base current. Can y'all see that? Anybody got questions? So very small base current is going to control a very large collector current. And notice how close these are. So this is 10.519 milliamps. This is 10.414 milliamps. So the emitter current is slightly greater than the collector current. But since we're going to be dealing with a lot of approximation, a lot of tolerances, for most of our math, we're just going to say these guys are equal to each other because they're so close, and it won't make any difference in our it won't make that much difference in our calculation. So as base current goes up, collector current goes up. As base current goes down, So here's base current. Base current is going up. Sorry, base current is going down, so collector current is going down. Over here, base current is going up and collector current is going up. So like I said, guys, this is free to use. So you draw your diagrams. It's not very hard to do. And then what you can do from then is you can actually simulate what will happen with these, especially in a DC environment. That's called Multisim. It's a free online circuit simulator. So y'all can sign up for this guy. All you need is your email address and a password. And then you can go to circuits. And then once you go to circuits, you can start designing. I mean, you can save them also. So you can save these circuits, and you can come back like I just did. I drew that circuit last night. Saturation. So we saw both of these. Saturation, the transistor acts like a closed switch. So if I put enough base current in here, so what I'm going to do is I'm going to make this a variable power supply.
So, Mr. Raymond, this is the slides that we have available. All this is hot linked in there too.
Right, the link's there, but when you click on the link on Multisim, it'll take you into the login screen, and you'll have to, create a new account, and then email. You'll have to enter your email account and password.
Okay.
And then after that, this is free to you, and it's a really neat application. So what I'm going to do is I'm going to put a collector resistor right here. And this emitter power, this collector power supply, it's not going to be variable, it's going to be fixed. So let's say this is 0 to 5 volts. Well, when I'm sitting here at 0, if I put 0 volts over here, that means that would be 0 and a 0, so we'd have no base current. If we have no base current, it means there's no collector current. If we have no collector current, that means the transistor is technically operating. Now we know it's not perfect. There's no such thing as a perfect semiconductor. So there'll be some voltage there. I mean, it's going to be some current, but it's going to be linkage current. So what happens is your transistor is acting like an open switch if you have no base current. Or if the voltage we get on this side is not enough to get, if it's silicone, to get approximately 7/10 of a volt right there. So that means I'll start off at 0 volts. If I put 0 volts, the transistor will be cut off 0, 0.1, 0.2, 0.3, 0.4, 0.5. Then what will happen is when we get around 0.5, 0.6, 0.7, then that's going to forward bias this and we'll have current. But right now, let's just use 0. If this guy acts like an open switch, that means I would measure 15 volts across the transistor, and I would measure 0 volts across that voltage drop across the resistor because there's no current flow through it. This is called cutoff. So in cutoff, the transistor acts like an open switch. Now come over here and start increasing this voltage. Current goes up, 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 to eventually where this collector resistor up here is going to drop. It's going to get enough current flow through it to cause it to drop the entire voltage. So if this resistor, if there's enough current flow through it, so that resistor drops 15 volts, then what happens is now there's going to be 0 volts left to drop across your transistor. So your transistor is acting like a closed switch. Now it's not. You'll never measure 0 volts across the transistor even when it's saturated, but it's going to be, normally we say if it's less than 1 volt. So normally if we say the voltage collector to emitter, if it's less than 1 volt, we say the transistor is saturated. So if I can switch it between saturation and cutoff, then we can do things. We can turn things off and on, and like the presentation made, this could be digital. So this would be digital, where we only have off and on. So if I switch it between off and on, this transistor is going to act like a switch. If I'm between saturation and I'm between cutoff, then the transistor is going to act like one of these. It's going to act like a rheostat. But what we're doing is we're electronically controlling this with base current. So this is where your amplifiers operate is, your stereo amplifiers, like out in your car, or your speakers on your cell phone. This is going to use these bipolar transistors or FETs, and we'll look at that. And it's going to make them operate in what we call the active region. So in the active region, the transistor acts like a rheostat. And what do we do with a rheostat? We use the rheostat to control a current. We use a potentiometer to control a voltage. We use a rheostat to control a current. And of course, that was the same simulation I just showed y'all. I carried it between saturation and cutoff. I should have left it open, guys. I don't know why I closed it. I might have. Let's see. I did. So right now, let me, in fact, my simulation is still running. So right now, I've only got 14.95 millivolts dropped across my transistor. So I got 45.54 millivolts. This is measured on the bottom side of the resistor, dropped across the transistor. So it means there's roughly 15 volts being dropped across the collector resistor. If I come over here and move it the other way, over to this side, then we see there's 15 volts dropped across the transistor. So the transistor is in cutoff, which means this resistor is dropping 0 volts. So this voltage up here, don't get it confused. That's where it's measuring. It's measuring at the transistor. I had to spread it out so I could put all these measurements in there for it. So now the transistor's cut off. Now it's operating in the active region. That means if I put a varying signal on it here, it's going to vary proportional to the input. And then when I get it on this side, the transistor is saturated. So there's only 45.45 millivolts being dropped across the transistor. So like I said, you're not going to have perfect cutoff and you're not going to have perfect saturation because these are not open switches and these are not closed switches. But when I'm saturated, the transistor is going to drop less than a volt. So we assume less than a volt to be saturated. If we measure the applied voltage, which we will, because our meter won't measure that, then we say this is in cutoff. If it's somewhere between the applied voltage across the transistor and, of course, 0 volts or less than 1 volt, it's going to be in what we call the active region. When it's in the active region, then I could literally put a varying signal into this, and then, of course, the output would perform proportion. So let me pause it this time. So it's been running for quite a while. So these are the 3 regions we can operate. So just for rule of thumb, saturation, transistor acts like a closed switch. So what we're going to do, if the voltage drop is less than 1 volt, we're going to be considered it saturated. Cutoff, that transistor acts like an open switch. And you will measure really, really close to the collector voltage across the transistor. In the active region, this is where your audio amplifier is operating. BJD characteristics and parameters. So we'll look at this. When a transistor is operating in the active region, the collector current is proportional to the base current. We refer to this as the DC beta. And this is the abbreviation right here. is the current gain of a transistor and is the ratio of the DC collector current to the DC base current. So basically it's calculated by IC, so beta DC would equal to IC divided by IB. And beta has no unit. So if I know beta, then I can say, okay, if I got a beta of 10, that means if my base current is equal to 10 milliamps, which it won't be, or let's say 1 milliamp, then my collector current would be equal to 10 milliamps. So all it is a multiplier or a divider. So if I know my collector current, so IC would equal, if I transpose the equation, would be equal to IB times beta. All right. And then IB would be equal to IC divided by beta. And beta is a number. It's not a multiplier. I'm sorry. It doesn't have a unit. Beta does not have a unit. It's either a multiplier or a divider, so you can calculate these other things. Once established, beta is a constant ratio called the current gain, is usually designated H sub FE in the data sheet, which stands for higher forward transfer ratio with the emitter common. This is, we'll look for that in the data sheet, but it'll also be called current gain. So if we come up here and we so over here in reference material, we got a whole section on data sheets because it's so big. The transistor we're going to be dealing with mostly is a 2N 3904. So a bunch of the transistors start off with 2N. So notice generically diodes start off with 1N, which means it's got 1P in junction. A lot of your transistors start off with 2N, which means it's got 2P in junctions, right? Here's the 3904. Here's the actual data sheet. And what I'm going to do is I'm going to come down here and look for H sub FE. There it is. And you can see this guy's all over the place, depending on the collector current and emitter current. The minimum beta this guy should ever expect would be 30. The maximum we would probably ever measure would be 300. And so what we'll figure out later on is how I can actually set the beta to where I want it to be with bias. I just know I cannot set the beta less than 300, and I know I cannot establish a beta greater than 100. Does that make sense? So when we get into amplifiers, we'll see that we set the beta where we want it to be. So once established, beta is a constant ratio called, once it's established, not once we establish a beta of 30, then it would be a constant ratio. Once we establish a beta of 50, then it would be a constant ratio once it's been established. So here's the formulas we already looked at. So beta DC is equal to IC over IB. So IC would be equal to IB beta times IB. And then IB would be equal to IC over IB. And all these formulas should be in the transistor section of your formula sheet. DC alpha is the ratio of the collector current to the emitter current, so it'd be IC over IE. Since IE is always larger than IC, alpha will always be less than 1. This is not given in data sheets. I've never seen one that gives it in a data sheet. So what we do is we usually calculate it. So if we measured IC and IE, we could use that. Or we can look up beta on the data sheet. So it's going to be beta over beta plus 1. So this makes this is always going to be less than 1. So once we get that, we can calculate IC or IE with this. We'll only talk about alpha when we get into a transistor amplifier arrangement that we call a common collector. The first transistors we'll look at, amplifier circuits we'll look at is going to be the common emitter, which is the most widely used transistor amplifying circuit. And then when we get into the common collector, we'll have to understand a little bit about alpha. Transistors, we need to know how we nomenclature these on diagrams, how we nomenclature these measurements. 3 DC voltages are for bias or transistors. These are reference to the circuit to ground or common. I need to make sure I get that. And this is circuit. So we'll reference the base voltage as VB. We'll represent the bias voltage on the emitter as VE. And we'll represent the voltage on the collector as DC. And these are measured directly to the lead. So this is going to be showing you on the next slide. So if I come over and take a meter and I measure between here and here, then what I'm measuring, am I measuring VB? If I take a meter and measure between here and here, now it doesn't make any sense because we have nothing in the emitter to common. But later on, we're going to put a resistor here and we'll talk about why. This will be VE. If I took a meter and measured between here and here, then I'm going to be measuring DC. Now, power supplies, we are going to duplicate that. So VCC, this means this would be the power supply that's referenced or connected toward the collector. VBB would be the power supply or the name of the power supply that we'll use when we reference the power supply connected to the base. I think that's on the next slide. The 3 DC voltages for bias transistors reference to the leads. So this is when we make a measurement between the leads. So base to emitter, and this is where you're going to hook the common of your meter on the one that's on the right. So base to emitter, it means I'll put the black lead of my emitter. I'll put the black lead on I'll put the black lead on the emitter. And then I'll come over here and I'll put the red lead on my meter. I'll connect it to the base. And I will measure my voltage base to emitter. When it's forward bias for an NPN, this is going to be equal to approximately 17. For a germanium, this should be approximately 3/10. We know that's not perfect. It's just basically a rule that we use in math because it varies with current. So once it conducts, it might start conducting at about 500 milliamp. Might start conducting that when we put about 500 millivolts on the base. It might be 600 when we saturate it. We might have like 1.1 volt there, but 0.7 of a volt is good enough for calculations. And we know now that our calculations are not going to be perfect, but they're going to be close enough so we can understand if the device is good or bad. The collector to base voltage, which means we would actually put this on the lead or a component connected to the lead. That bothers me too, where I'll come over here and I'll have this nice big resistor sitting right there, and this little old transistor sitting down here. These leads are close together, and y'all trying to get between these guys right there when I've got a resistor over here on the base, so I could put my lead on the big nice metal thing on the resistor, and I could go to the big nice metal connector on that. So that's one thing you're going to learn on transistors. It's very hard to measure across the lead. So this is the transistor that we're dealing with in here. This is a case we call a TO92 case. And these are solid wires, so when you hook these things up, I don't want you spreading and bending these leads over for your convenience. I want you to put these things, and I want you to put these things in consecutive holes on your thing. So this is a 39, look at how close those leads are together. So when I come in here and put this in a breadboard, I don't have a breadboard up here. I'm going to put these things in consecutive holes. What happens is students will come up here and they'll bend these things and they'll bend them. And then what happens is they'll break off right up here where they go into the transistor. So when you put these things when you put this thing into the trainer, you're going to put it into consecutive vertical lines, right? You understand that? Then, but you're going to have a resistor connected to it. So I'll have a resistor connected to the collector lead, so I don't have to get on the collector lead. I can get on the wall, the resistor that's connected to the lead. And you'll learn that real fast in transistors, that you very seldom can you get to the lead without doing what? Well, not bending them, just accidentally. You're over here looking at your meter, you slip off the lead, you touch two leads together, and you blow your transistor just like that. So I've seen students twist resistors together, leads, to get a certain thing on a trainer where they could just hook them in the same the hole, right? So here's our measurement. So like I said, I don't have to get on that little tiny lead on the base. All I've got, I can get on this resistor right here, and I can get on the lead on that resistor right there. And I would be measuring BCD. With where's my black lead button? So this is the one on the right. This is where you're going to put your meter common, so your voltage is a measure, right? You put it on the second lead. So here I would put my black lead right here, even though my drawing is, and over here I would put my red lead right there. Over here I would put my black lead on somewhere on the common. I don't even have to get that one. I don't even have to get that one on the lead. I mean, I can just put that on a common that's all over my circuit, right? And of course over here, if I wanted to measure this, then I could go from circuit common up to this resistor right here. Or if we got a resistor down there. Eventually we're going to put a resistor down there and we'll talk about why. Okay guys, I'm going to pause the lecture. So which voltage measurement would you think would determine what resistance the transistors operate? We have three regions: saturation,
Let's see.
cutoff, and active. Listen, somebody was saying something, but I couldn't hear you. Which measurement would determine what region the transistors operate in? Nobody knows? Yeah, we're trying. So what we're going to do is we're going to take a voltmeter and we can measure. There's a measurement we can make. One of these three right here that would tell us right off the bat if the transistor's cut off, if the transistor's saturated, or if we're in the active region. What measurement would that be? It's either going to be voltage collector to base, voltage base to emitter, or voltage collector to emitter. It's going to be one of these three measurements that I've got up here on my PowerPoint is going to determine, I can make this measurement and I can determine what region the transistor is operating. So which one would y'all think? I'm fixing to start calling names. So which one would you think, Jenna? No, what I'm trying to do is I'm trying to figure out which measurement I'm going to make over here to determine which region. So I can either make a measurement between the collector base or base to emitter or the collector to emitter. And when I make that measurement, I can tell what region it's in. So Lee, you out there, which one do you think? are active?
I'm not really sure either.
So what we have is we have basically we're going to operate the transistor like this. If we're cut off, the transistor is going to be acting like an open switch. If it's saturated, the transistor is going to be acting like the transistor is going to be acting like a closed switch, right? If it's cut off, the transistor is going to be acting like a rheostat. So to tell if a transistor is saturated, we would make this measurement right here. This would be the one. This is the one right there. If I measure less than 1 volt across the transistor, emitter, collector to emitter, less than 1 volt, then we're saturated. If I measure VCC, if it equals VCC, then the transistor's cut off. If it's operating between saturation and cut off, then the transistor is in the active region. So this measurement right here, this guy right here, measuring that measurement right there, that determines what region the transistor is operating. So I can tell with one measurement right off the bat, and this is one of the best tools that I've seen to try one of the first measurements we're going to make to figure out what region the transistor is operating. Because if it's operating in cutoff when it's supposed to be in the active region, that tells me something. If it's saturated and it's supposed to be in the active, it's telling me something, right? You understand that? So this is probably one of the most measurements we're going to make is this voltage collector to emitter to determine the region. So rule of thumb, less than 1 volt, saturated. If it's equal to VCC, that means if the transistor's dropping all the voltage, then RC can't be dropping any, which means there's no current flow in the circuit, right? Of course, there's going to be leakage current, but we can't even measure that because it's not an open switch. We say acts like, we don't say it is. So if all the voltage is across the collector to emitter, that means the transistor is cut off. There's no current flow through it because RC is not dropping any voltage. If it's less than 1 volt, it means RC is dropping all the voltage. So that means the collector current has got to be really high, right? You understand that? And then, of course, if it's in between the two, we say it's in the active region. So active region, by the way, we try to put it right in the center, and we'll look at that in a minute. Very important measurement. So basically, this is what we're going to treat the transistor. We're going to treat it like it's 2 different things, 2 different circuits. We're going to say, okay, we got the base circuit. We'll treat that like a diode between the base. And then on the other side, on the emitter collector side, we're going to calculate the collector current by using this guy right here. We're going to use the beta times IB. And then that'll give us a good idea of what the collector current is. And then we'll use that to solve for the right-hand side. So here's some reform. And these are, guys, this is nothing but laws we already know. The only new one that we're going to pick up is this gain. And we've talked about gain before. So we know that my emitter voltage, my base to emitter is going to be, for silicone, it's going to be approximately 7/10 of a volt. We know that my base resistor has to drop whatever my base voltage is minus my base to emitter voltage. Right? So what we're saying is if I come over here and then I have a DC voltage source, and this right here is plus 5 volts, and this is a 1K resistor. I know that my base current is going, this guy's going to drop approximately 4.3 volts. I know the size of the resistor, it's in series with the base. So I know I can calculate my base current by taking 4.3 and divide it by 1K. And that would give me my base current. VC, we know that we have two series elements right here, right? Y'all understand that? So that means if I come over here on the right hand side and I put a DC source, and this right here is going to be VCC, this would be VBD. The emitter's common, so it's got 0 volts on it. Then if we're going to call this RC, then I know if this is 15 volts, then 15 volts has to be the sum of the voltage drop across RC. So we know that VCC is going to have to equal to RVRC. Who's I could draw this right? According to Kirchhoff's law. We know that VCC is going to have to equal to VRC plus VCE. It's got to equal. It's got to equal to 15 volts. So what that means, if I can calculate the voltage drop across RC, then VCE is going to have to be equal to VCC minus VRC. So normally what we'll do is we can get the collector current. We're going to use that current to calculate the voltage drop across RC. Then we can use RC to calculate voltage collector to emitter. Voltage collector to emitter is going to be here. So it's going to be whatever voltage I measure on the collector minus whatever voltage I measure on the emitter. Now right now we have nothing in the emitter circuit because we're just learning this, but later on we're going to put a resistor down there. VC would be equal to VCC minus RC times IC. So what we're doing is we're calculating the voltage drop. Voltage collector emitter would be DC minus VE. Voltage collector to base would be VC minus VD. And then voltage base to emitter would be VE minus VE. So let's calculate this. So where would I start at? Tell me where I would start. Now we're going to use a beta of 100. So where would I start? What do I know? What in this circuit do I know? Do I know IC? No, I don't know IC. Do I know IB yet? No, I don't know IB, but I know how I can calculate IB because I know this circuit right here. I absolutely know this circuit right here. I know that 5 volts has to be dropped in that loop. 5 volts has to be dropped in that series loop. And what I do is I know that this guy right here, if it's silicone, I know that this guy right here is going to drop approximately 0.7 volts. So what does that mean? If this guy's dropping 0.7 volts, the sum of these two has to equal to 5 volts, then I know this resistor right here is going to drop 4.3 volts. Or approximately, but this is going to be close enough for calculation. So now I can calculate the current flow through RB. The current flow is here. This is the series loop. So whatever current flow is going through RB is going to be the current flow that's going through IB. So what would IB be equal to? IB would be equal to 4.3 divided by 100. So somebody give that to me. I'm waiting. Huh?
Like 430 microamp.
Now 430 microns. Here's coming. Okay, so what do I know now? I know the base current. I've given you the beta. So I know IC, this is the new formula. IC would be equal to IB times beta. So I'd say IC would be equal to 430 micro times 100. What would I see? I'm waiting.
43 milli.
It's gonna be 43 milli, right?
Yes.
Okay, now I know IC. Well, now we're over here on this side. We're through this side. Now we're over here on this loop over here. Well, I know IC is 43 milliamps. I know the size of RC. So VRC is going to be equal to 100 ohms times 43 milli. So what's VRC going to equal to? All right. I think, Lee, you're the only one doing it.
0.3.
43.
4.3 volts.
Yes, sir.
Okay, so this guy's dropping 4.3 volts. You have to drop 10 volts, excuse me. So what would be the voltage collector and emitter? So voltage collector's emitter, according to the Kirchhoff's law, this guy and this guy's got to drop 10 volts. So it's going to drop what? 5.7 volts. So what region is the transistor operating in? Is it operating in the active region? Is it operating in cutoff? Or is it operating in saturation? Is it less than 1 volt?
It's going to be active, isn't it?
Is it equal to 10 volts? No. I just think operating in the active region. So the power dissipated by the transistor. So, by the way, transistors are usually given the designator T because T was took up by transistors by transformers a long time ago. So they started using letters in the alphabet. So on a schematic, your transistors are going to be labeled Q. Odds are. So my power, the power of Q1 is going to be equal to 5.7 times 43 milli. So this is how much power my transistor is going to have to dissipate. And that's very, very important to know because it's a solid state device. So we have to know, if we know the voltage of collector to emitter, and we know the current flow through the collector, by the way, the collector is the reverse bias junction, so it's the one that's dropping all the voltage. The base to emitter is going to drop about 0.7 of a volt. So that 5.7 volts is being dropped in the collector junction. So the collector junction is the one that's going to drop all, and it's going to get hotter. So we'll look at that later on when we start heat sinking and stuff like that. So when I start looking at some transistors, if my camera's still up, I don't see it. Oh, here it is. So this is one of the cases, and it looks like it's only got 2 leads, but it's got 3 because this whole outside is the collector. Because the collector is the one that gets the hottest, so it's the one we want to expose to the atmosphere. On this case right here, you can see this on the camera. Oh, it's corroded. But this lead right here is connected directly to the chassis. I mean, to the actual case. These two right here are insulated, so this right here is the collector. So the collector is the junction that gets the hottest. So if I've got a metal tab that comes out of it right there, that metal tab is going to be the collector. So right off the bat, I know which lead is the collector. So I could take an ohm meter and put it right here and start touching these three leads. Then I can find the collector. By the way, on these three terminal devices, the emitter don't necessarily have to be in the center. The base doesn't necessarily have to be in the center, even though it's in the center of the diagram. So we'll show y'all in a minute how you can actually identify these leads and check a transistor with an ohm meter on the diode set. It's only when I run into these where I really got a problem. These little cases like this, because which one is the base, which one's the emitter, and which one's the collector, I have no idea. It's up to the manufacturer which lead they assign to these, what lead they assign here. So I'll show y'all how we can actually identify the leads with an ohm meter. I just do that in a moment. So this is these are not given to you, but using your beta, you can set them up. This is what we call a characteristic curve for a transistor. And what we do is down here, this is going to be on this axis. This is going to be your voltage collector to emitter. And up here, up this axis, this is going to be IC. And then over here, these are going to be IB. The transistor curves vary basically the same. They have a slight upper slope because of the internal resistance of the actual transistor itself. So that means we'll come over here, and then once we turn it on, then this guy here is going to be fairly level. And then what I can do is I can see, okay, I can get a feel of what the transistor is going to do. And then what we can do later on, we'll see that we can put a slope between saturation and cutoff. And then we can come up here and actually see what this thing will do when it comes up and we actually put it in an active circuit. This is a transistor load line, right? So these are actually, and we used to have a curve tracer in here where we could actually put it on an oscilloscope and put a transistor on there, and it would develop these for us. Normally we use beta, and if you use beta, you'll end up with load lines that look like this. They'll come straight across. But what you have to realize, it's going to be a slant, right? It's just like when we talk about transistor, the characteristic curve for diodes. It actually starts off and has a slight slant, and it goes up like this. But for calculation purposes, we say when this thing gets to 7/10 of a volt, it comes up and goes straight up, because we know that it's not going to be precise, right? You understand that? We know that all our math is, in semiconductors, your math is not perfect. Your math is perfect, but your components are not. But what we're going to find out is our math is going to, so if I come back to this circuit right here, if I hook up this circuit and I use a 2N3904, which has a typical beta of around 100, is this going to measure 5.7? No, it's not going to. Voltage collector emitter? No, it's not going to measure 5.7, but it's going to be close, right? You understand? It's going to be close enough that I can tell if the circuit's right. Because what's the odds of this 10K being a 10K? Little to none, right? What's the odds of a 100 ohm being exactly 100 ohms? Little to none. What's the odds of that transistor having an exact beta of 100? Slim to none, right? You understand that? But it's going to be close enough when I measure these voltages. This is not going to measure 7/10 of a volt. It's going to measure close to it, but it's not going to measure 7/10. This power supply is going to be, you see me adjust these. I can measure the 5 volt power supply on our trainer, and it's not going to measure exactly 5 volts. So even regulated power supplies are not going to measure exactly what they're stated as. It's going to be pretty close to it. So switch. So transistors as a switch. The book covers this. We're going to tell you how to actually set this up. This circuit design is not very, very complicated. The transistor switch between cutoff and saturation. This is the most popular transistor circuit. If you can think about all the memory you have in your computer, it's nothing but the little switches. So all your pixels on your screen, your screen are going to be with nothing turned off and on with little switches. So by far, the most popular circuit for a transistor is being used as a switch. So every digital device you have has thousands or billions of transistors. Some of our microprocessors now, it's just unbelievable how many transistors they can get in there. Of course, they don't have to, they're not very, all they're trying to do is give us ones and zeros. So what determines the size of a water valve would be how much flow it's trying to control. So what determines the size of a transistor is how much current flow it's trying to control. So I come up here and look at these different transistors. I know for a fact that this guy can control a lot more current flow than this guy right here. So this guy is going to be controlling amps. This guy is going to be controlling milliamps, right? You understand? So the size of the transistor basically will tell you, how much current it can control. How much current flow can we put through that thing and not burn it up? Because it is going to drop a voltage. So this is a type of case. We'll look at this. This is a TO3 case. This is a TO92 case. And they don't define the case style does not, and this don't even have to be a transistor. This could be a voltage regulator. So just because you see a 3-terminal device, don't tell you what it is. Anything that requires 3 leads could be in a case like this. So this could be an SCR, or this could be a triac, or this could be a voltage regulator, or this could be a transistor, or this could be a bipolar transistor, this could be a field effect transistor. If it was an FET, I wouldn't be handling it like this, by the way, because those are susceptible to static discharge. So just because you see one of these cases don't mean it's a transistor. It could be a lot of things. That's when you would basically make sure you look up the part number. Most popular, this is, No, there's no power on it. The problem we have with FETs, yeah, those FETs. FETs, field effect transistors are susceptible to damage by static discharges. So anybody that works with FETs are going to use they should use static bands or not handle them a lot. Bipolar transistors, these guys use a current to control the current. So that means these guys, odds are you can't hurt these things with. You're not going to discharge to them because static electricity does not produce a current flow, right? Okay, so it's that. So to design a saturated switch, so this is not in the textbook. Establish the voltage and current that's required by the device to be turned on and off. We'll call this IC sat. So what we're going to do is we're going to saturate the transistor. To turn it on, we're going to saturate the transistor. To cut it off, we're going to cut off the transistor. Choose a transistor that will supply the current and saturate it and block the voltage needed by the device when the transistor is cut off. So what we have in data sheets is we have these measurements right here. We have what we call VCEO. So this would be the voltage collector to emitter with the base open. So what we're having, this means the transistor is going to be cut off because if the base is open, there is absolutely no base current. If there's no base current, then the transistor is cut off. Yet, so if it's cut off, then what is happening, it's dropping all the voltage. So if I come over here and start increasing this voltage, increasing this voltage, increasing this voltage, increasing this voltage, sooner or later, I'm going to cause this transistor to conduct. It's going to be dropping a lot of voltage and it's going to burn up. So this is kind of like the PIV rating on a diode. So these are the voltages that you can reverse bias a junction with, and not cause it to be damaged. So this is a very, very important rating. So if I come back over here and look at my data sheet again, which I've already closed out, and there's some ratings in here. So the data sheet, so 3904, which is the one we're dealing with mostly right now. And it starts off in the absolute maximum rating right here. So V sub CEO is 40 volts. That means this guy is guaranteed, when you cut it off, it's guaranteed that it can block 40 volts. If you exceed the voltage collector to emitter, then the transistor could start conducting and it could mess it up. The problem with solid state devices is they can go bad 3 different ways. They can open, they can short, or they become leaky, which means they don't operate the way they're supposed to. So this is the breakover voltage, collector to emitter for the 3904. Now it's going to be okay with us. The biggest power supplies we have is a plus 12 and a minus 12. If you hook them in series, you get plus 24 volts. So there's no way in the world we can mess this up with our train, unless we hook it up to the AC supply. So what we'll make sure, if I was going to turn on a light, I would need to know how much current it needs and what, of course, the current is going to be controlled by the voltage on that, right? You understand? If I need to turn on an LED, then we're going to look for roughly 2 volts across the LED, and of course, what we're going to do with the transistor. So what we do is we choose a transistor that will be able to supply the current when it's saturated. So in the data sheet, the current it provides, if I didn't close it out again, I bet I did. Need to leave it open. Oh, here it is. So right here, we're looking for this current right here, IC right here. This is the maximum current this thing can control. That's 200 milliamps. So that means I'm gonna have, if I'm gonna saturate or use a 3904 to turn something on or turn something off, then it cannot conduct more than 200 milliamps. If it does, then we can mess our transistor up. So IBSAT, this is going to be IC divided by beta minimum. Now, why we're going to choose beta minimum is that we want to assure that the transistor saturates. So of all those betas that we listed, the only one that's guaranteed is beta minimum. So for the 3904, then my minimum beta I would use, so here's beta, HFFD, I would use 30. If I use 30 to calculate this thing, then it will saturate. We use the lowest because it's guaranteed. This is not guaranteed. 300 is not guaranteed. 60 is not guaranteed. 100 is not guaranteed. 70 is not guaranteed, but the minimum is guaranteed. So that'd be like the minimum wage. So if you go to work for in the state of Alabama, you're guaranteed at least 7 something an hour, right? Y'all understand that? You're not guaranteed anything higher than that. Now, hopefully, we want to do that, but so that would be like minimum wage. So you're guaranteed that. So if I was going to go for a job and I was trying to figure out, my bills and stuff like that, then I would work on minimum wage, and then that way I would know if I got a job, I would be able to pay my bills. Right? RB maximum, RV base. So RB, this is the maximum resistor we would choose. I take my calculated my voltage across VBB, which is the power supply on the base, and then I would divide it by my saturated base current, and then I would always round this down. If I round it up, I would be going away from minimum beta. If I round it down, then I would guarantee saturation. And I don't have electronic workbench, but we do have that. So let's say we want to transit. I should have a circuit in here, but let me go ahead and pause it on okay. And then I'm gonna put a switch in here, and let's design one. So we're gonna do this instead of using two voltage sources. We're gonna use. Let's do two first. So let's say I come over here and I'm gonna put a base resistor. Call it CT right now. And then I'm gonna come over here and put a transistor. We're gonna connect the emitter to common right now. And then I'm gonna come up here and I'm gonna do an LED. So we'll say the LED VF, let's say it's 2 volts, and it's to light it up real nice and bright, let's say 15 milliamps. Now, this thing, if we exceed VF, it's a short circuit, so what we'll do is we'll come up here and put a series dropping resistor. And then we'll take this back to, let's say it's going to equal to 10 volts. And this right here is equal. Let's say VDD is going to be equal to 0 or 5 volts. So 5 volts should saturate it, 0 volts should turn it off. So, what will we do first? We're going to figure out what was saturated. So what I'm going to do is I'm going to say 5 volts should saturate it. So I say CRB would equal to 4.3 volts. And at what current? Let's redo this. First of all, we'll give you. So I'm giving you IC sat. So it's going to be equal to 15 milliamps. We're okay? So what size is RC? B, we're going to assume voltage collector to emitter. We're going to set it to saturate, so it's going to be equal to approximately 0 volts. So what size resistor should I use for RC?
What is the 2.0? I see VF 2.0 at 15 milliamps. What is 2.0? What is that? 2 volts, 2 amps, 2 ohms?
That's right. So LEDs are rated in two things. They're rated in their VF. So it said VF, I'm sorry. So it said VF. So VF, for rule of thumb, if you don't know the VF of a LED, we usually use 2 volts. And then that's going to be at a current. So the current that I said was 15 milliamps. So what size RC should we use? It's a series circuit, guys, and this is what you're trying to see. This is more complicated than it is. So if I got back into DC and I come over here and I said, okay, I got 2 resistors right here. Well, actually, I got 3. But the transistor we're going to saturate. So I basically got 2 resistors. Here's RC, right? You understand? I'm giving you the diode. I say, okay, this guy is going to drop 2 volts at 15 milliamps. And up here at the top, I'm applying 10 volts. This is DC. I'm using Kirchhoff's law. I said, okay, the sums of the voltage drops in a series circuit have to equal to the applied voltage. The current flow in a series circuit is the same. So I've given you the current, I'm giving you the voltage drop right here. So I know this guy right here's got to drop, I got to choose a resistor that's going to drop 8 volts, 2 volts, 8 volts, 10 volts at 15 milliamps. So what size resistor would I use with it? R is equal to V over I. So R would be equal to V, which is 8 over 15 milli. Hopefully when you got out of DC, you said, I'm through with DC. I don't need to know any of these formulas.
533 ohms.
What's that? 533 ohms? Yes, no?
Yes, sir. 533.3, whatever.
Okay. Well, the problem we have is that there's no such thing as a 533 ohm resistor. So what am I going to do?
Go to the data sheet.
Look what?
Go to the
By the way, y'all know when you're here, you have access. You still have a tab up there, so you could go back over to. If I can find myself. So you still have your content tab right here. So right here you got your. So right here you got your room, right? You understand that? And then you can always just go back over to your content tab. And then you can come up here and I can go up to reference material. And I can look at the standard.
It'll be 560 plus or minus 5%.
Plus or minus 5%, right? So we look at our standard resistor chart, right? And then we would round. And then we would come back and recalculate. So I'd say, okay, the 5%, closest thing I got to 533, which means we would probably round down, is I could use a 510 ohm resistor. No.
You say always go up, so that'll be 560.
Well, no, we could go up or we could go down. So what we're doing is 15 milliamps is not the maximum. So normally if you look at the maximum current flow, it would be quite a bit more than that. But we can round up or round down. It doesn't make any difference. So if we have 533, that would actually round down, right? You understand that? Yes or no? So what we're going to do is we're going to round this resistor. We're not going to round up. We're not going to round down. We're going to round this resistor. So 533 would round down, we would go down, right? You understand that? If it was over 550, we would round up. So 510 ohms. But the 560 would have worked and the 510 would have worked. This would have made the LED a little brighter. This is going to make the LED a little dimmer, but you're not going to be able to tell the difference. So that's a good point. So I'm going to choose a 510 ohm resistor. So that's going to be 510, right? You understand? So how much voltage is it going to drop now? So 510, right? Times 15 milliamps. I'm sorry, 510. This guy's going to drop 2 volts. So now, this guy's still going to drop the same thing. So what's the current going to be though? So now it's going to be 8 divided by 510. So what's that going to be? That's 8. I don't know where that came from though.
Like 15.68, so just like, I don't know, 15.7 milliamps.
What's that? 15 point,
like 15.7.
okay, so 16 milliamp. Then I'm gonna calculate IB to saturated. Is going to be equal to, one thing I didn't give you is I didn't give you the beta. So let's use 100 for the beta. So IB sat is going to be equal to 16 milliamps divided by 100. Y'all know what this is. So what we're doing is we're using IB is equal to IC divided by beta. What I did-
Like 160 micro.
Yeah, about 160 micro. Calculated IB sat equals 160 micro. So what size would I use for RB? Yeah, y'all thought y'all was gonna get away from all this when you got out of DC, didn't you? But the only formula that we've added is beta. Is this thing called beta, right? It's instead of a, let me redo this, guys. Stop your math for a second. All right. Let's use a beta 30. And I'll show you why in a second. What unit does beta have? Beta does not have a unit. It's either a multiplier or divider. Like says, I'm going to triple your salary. You say, okay, I'm going to get a $3 an hour raise.
And your beta is always gathered off the data sheets, correct?
Right. Exactly right. And what we're doing is we're using minimum beta because minimum beta is guaranteed. So what we're doing is we're doing this for a 3904. And the minimum beta is 30. So that means if the beta is greater than 30, you can't saturate a transistor more than it's saturated. So as soon as it drops about 0 volts, it don't make any difference how much base current you put into it after that. You can't close the switch more than it's closed, right? You understand? So once the transistor is saturated, then you can't get more out of a transistor because now it's acting like a closed switch. So if we put more base current than is required to saturate it, it's not going to make any difference. All we're trying to do is guarantee that it's going to saturate no matter what we do, as long as I put about 5 volts on the input. So even the 5 volts is not guaranteed to be perfect. So that's why we're going to make sure. So if I design it around exactly 5 volts and exactly this and exactly that, then it may or may not saturate. But if we design, what we're trying to do is design it so it always saturates. So I could use a beta of 40, but that means sometimes it would saturate, sometimes it wouldn't. It might saturate in the summer, but not saturate in the winter. We had a scale that we had at a plant down in Calera, electronic scale that stopped working on cold nights. But by the time we would load up, we would come in at 8 o'clock, and by the time we load up, we'd get down there, the scale itself was in a building that was outside, and it wasn't insulated. So what would happen is the sun would start shining on it, it would heat up, and so the scale was always working when we got down. So that was a big deal. Come to find out that they did something very simple. They took for granted something that instead of an always, they used a usually, and of course that was causing it problems. So And then once we finally figured it out, we were okay. But yeah, that was a hard one to troubleshoot. So we're going 30. So I'd say I see. So we're doing away with this. And we're dividing this by 30, guys. I forgot to do that. So what would that come up and give me now? So 16 milli divided by 30. Somebody help me. Milli divided by 30. But you got to give it to me in milli or micro. Right?
533 micro.
Okay, so what size would RB be? 4.3 at 433 micro. That's correct. And I can't get my calculator up right now. Oh, yes, I can. Hold on. So 8,067 ohms. Is that okay? We calculate, first of all, we calculate the base current. So I would take, what was I mean, 16 milli. And then I would divide it by the beta, which is 30. That gives me my collector current, 533 microohms. Okay. And then I want R is equal to V over I. So I know we want this resistor right here to drop 4.3 volts. So that would be, R would be equal to V, which would be 4.3 divided by 533 times 10 to the negative 6. That comes up and gives me 8,067 ohms. Or 8,068 ohms. There's no such thing as an 8,068 ohms. So what we're going to do on this guy, guys, to assure that we're going to saturate, then on this we're going to always round down. So I look at my standard resistor chart, right here, 8,000, so here we're in K, right? So what I would use here is I would use the 7 point, so what did we come up with? 7.5K. Is that right?
So you always round down on this one?
Yeah, because what we're trying to do is we're going to guarantee saturation. That's what we're trying to do. So we guaranteed we use minimum beta of 30. If we round up, then that means we're not going to get minimum beta. It might be a beta of 32, which is no longer guaranteed. So of all the betas on the beta chart, the only one that is guaranteed is minimum beta. So if we round down, we'll get more current through, we'll get more base current through than we need to establish minimum beta. That makes sense? So yeah, we'll round down here. So we calculated 867 ohms. So I won't use an 8K, I'd use, what did I say, 7.5K?
Yeah, 7.5.
So what laws did we do? All we used is this Kirchhoff law, except for the beta formula. I mean, the beta, we used beta to calculate what we would need for the saturated base current, and then we rounded up resistance down. We could do this with a light bulb. We could do this with a relay. The only problem with a relay, guys, and I'll have to show y'all this when we come back into campus. If y'all try, I hope y'all wouldn't try to write that down. So we could do it this way too. We could come up here and do this with one voltage solar. So I could have came over here and did this like this. And then I could use I'm going to put my transistor right here. Guess I need to move it over a little bit. I'll just come over to it. See, this done a lot. So with the switch closed, you put 0 volts on the base, and the transistor would turn off. When you close the switch, then we would have bias, but here we wouldn't calculate it for 2 voltages. If this was 15 volts, then we'd have to choose that resistor here to drop 14.3 volts. And so that's one way we could do it. And here we only have to use one power supply. We could use this to bring in, this load could be any resistive load. So it could be a light bulb. It could be our load. It could be a relay. So we could come up here and actually turn on a relay. And we've done this several times. Now what we need to know about the relays are going to be either rated as a volt and current. But the problem is that normally what we need to know to calculate this is we need to know the actual resistance that it has. So if you got a 24 volt relay that's rated at 1 amp, of course we couldn't run it, let's say rated at 100 milliamps, then if it's rated at 24 volts here, then of course we wouldn't need, all we need to do is make sure we have 24 volts up here, right? And so we wouldn't necessarily have to have a drop in resistance. But if all I had was 24 volts and I had a 12 volt relay, then you could put a drop in resistor in there, right? Does that make sense? The only problem we have with relays is when you de-energize it, when you cut off these things, these guys put out. So what we got on a DC relay is so the only thing that limits the current in a DC relay is the resistance of the wire. So DC relays are going to have a lot of turns of wire. And so what happens is anytime we come up here and we put current through a conductor, it sets up a magnetic field. And if you have conductors that's going through O and O, then what happens is your magnetic field combines. Now what happens is you got all these turns of wire out there. And then you turn this thing off. You turn this relay off. Well, what happens is that magnetic field comes collapsing down. So we used all these turns of wire to get R up so we wouldn't burn things up, right? You understand that? They're very small gauge wires. But when I turn it off, that magnetic field comes collapsing down in the wires. So what we have is we have a magnetic field. We have a bunch of turns of wire. And then we got motion, the magnetic field. So when we turn this thing off, the magnetic field comes collapsing back there. And the amount is determined by the strength of the field This is what kills us, the number of conductor loops. And then the third.
So you're talking about using the coil,
Yeah.
using the coil in the relay as a resistor, right?
No, what we're talking about is what we have to do on our transistor to keep from blowing it up. So what happens is when we turn that so we saturate the transistor, relay comes in, closes its contacts, right? But what happens is when we turn the transistor off, that magnetic field collapses down into all those turns of wire. So what happens, it creates an electromotive force that is extremely high. We'll look at this. We'll do a neon bulb that takes about 90 volts to turn it on. I'll charge that coil up on 12 volts. I'll discharge it, and that neon light bulb will come on, which means that when that relay discharged, when that coil discharged, it discharged over 90 volts. Well, the problem is that would blow my relay up. I mean, not my relay, my transistor up, because what we just exceeded was this voltage collector to emitter with this thing open. So the 2N3904 is only rated at 60 volts. So that relay discharges, it outputs 90 volts. The transistor can only block 60 volts, and you just blew your transistor. So anytime on a saturated switch, anytime you use an inductive load like a relay, then you're going to have to put a diode across it right here. And what we'll do is we'll reverse bias it. And we call this a flyback diode, so plus 24 volts is okay, right? You understand? But when I turn the transistor off, my discharge is, instead of the magnetic field going out, it's dropping back. So this counter EMF is in the opposite direction. So the counter EMF would be shorted out through the diode. Now the diode, the coil has a lot of DC resistance, so this is not going to hurt the diode. But what it does, it don't prevent this. So what would happen if I didn't have that diode? As soon as I turn that transistor off, we would pop it every time. And sometimes you'll actually see the diode down here. So you can buy transistors with that counter EMF diode inside the package, which is good. And I'll show y'all some of those. But yeah, so anytime you're doing something, anytime on a saturated switch that you're doing something that's got a lot of turns of wire in it, then you're going to have to put that diode in there. We had a big old chain train printer that could do 2,400, 132 character lines of print every minute. That thing used these things right here, and we had one where the transistor went out, and we replaced the transistor, and we didn't check this flyback diode. And when we put it back in there, it just did what? It just popped it the second time. And the problem is the counter EMF diode was gone out. So resistive loads, we have no problem. These relays, these guys have what we call inductive loads. We can charge them. If you take AC, you'll find out that you can charge these things called inductors. But the problem is when we turn it off, and all that magnetic field comes collapsing back into those coils of wire, it generates an EMF that would wipe out your transistor. So you'll see that all the time. So if you're out there and you're seeing a transistor, and we do this all the time, guys, so even on PLCs. So when y'all come on campus, I'll show y'all some of the relays over there on our manufacturing line, and I'll show y'all these diodes. This does not apply to AC, so we don't have to have counter EMF on AC. But any DC circuit, if we're dealing with inductive loads like capacitors or coils of wire or something like that, then we're going to have to put the diode in there. And you put the diode in there reverse bias to the source. So notice I have the negative pointing toward the plus 24 volts. So during normal operation, the actual current flow is up through the relay. When I turn my transistor off, the counter EMF will be dissipated through the diode. And it's not going to hurt the diode, guys, because, like I said, the resistor has a lot of R in it, so it's going to limit the current, but, and we'll show y'all this. So what I'll do is I'll use a coil, and I'll charge the coil up to about 12 volts. First of all, we'll look at the neon bulb, and we'll see that the neon bulb takes about 90 volts to turn it on. And then I'll hook it across this inductor, and then I'll charge it up to 12 volts. And when I turn it off, you'll see that neon bulb comes on, which means that thing had to discharge at least 90 volts to turn that bulb on. So we'll show y'all that next class. So saturated switch, guys, these guys are fairly easy to design, and we use them all over the place because what it does now is allows so the little switches that turn these things on. So out on your car, you can turn on your lights. Well, that little switch on your steering wheel, there's no way in the world those lights out there that's pulling 5 or 6 amps is coming up to that little tiny switch on your steering wheel or on your dash. So what are you doing? Well, what you're doing is you're saturating the switch. You're saturating a transistor out there. The transistor's turning on a relay, and then the relay's running your light. So you're seeing saturated switches all the time. Used to make small currents. So these are got devices, so I've seen, controls for lights where you just go up there and hit a little button on there and it turns on the light. Well, there's no way in the world that little button is doing what. There's no way in the world that little button is supplying the current that's required to control the light, but we could run that through a saturated switch and do that, which is pretty interesting. So this is switch design. I've started in there. By the way, these are, we talked a little bit about, in sensors, in digital sensors, basically you're using saturated switches, for a solid state sensor. So all these transducers we're looking at, all these, photoelectric transducers, all these, your inductive and your capacitive transducers or sensors. These guys, and we talked a little bit about it, either syncing or sourcing. Well, inside the sensor, it's either going to use a PNP or an NP intrinsic. So a PNP, so notice here, so this is a PNP. So notice the emitter is connected to plus. So what happens, and of course, the collector is connected to common. Here they got it down as ground. So all I've got to do is come over here and put a negative potential, and if I put enough on here to saturate this thing, then what this is going to do is it's going to place this plus whatever voltage is across the load, because the transistor is going to drop less than 1 volt. So PNP, this is going to be a sourcing sensor because it's providing what? The power source. Now, a syncing sensor, the load itself is connected to the positive, right? And then when we saturate the transistor, so this would be an NPN. So we're reverse biasing the collector. It's got a positive, right? So what would happen is when we saturate this, it's going to drop less than 1 volt, and this is going to turn the load on. But what we're doing here is the load is connected to plus, the sensor is providing the common. Over here, the load is connected to common, the sensor is providing the plus. So this right here would be what we call a syncing sensor, which we talked about. Well, this would be the actual output of the sensor. So if you actually looked at the sensor itself, this is the way those sensors sync. So this is why it's called a PNP sensor, because it uses a PNP transistor as the output. So this is why a syncing sensor is called an NPN, right? And a sourcing is called a PNP. So that's how these things got the name. So
I mean, I'm guessing that's going to be common on like a photocell and a light bulb, like on your garage with a photocell. That's kind of how that works.
right? Photocells on your, those might use, instead of using, if it's hooked up to 120, so NPN and PNP transistors don't work with AC, they work with DC. Later on, we'll look at a device called a triac, which basically does the same thing, but it'll switch AC. So normally, when your light is hooked up to 120 volts AC, then we know we're not using NPN or PNP because these guys work off DC. But on your car is a DC device, right? You understand? So you got all these sensors out there. I've got an auto dimming, my wife's car, it'll automatically, she puts her lights on auto and it'll automatically do what? Turn them on bright, dim, bright, dim. She's got mirrors on the side, that has a little caution that comes on if there's something up beside her that you can't see in your rearview mirror. And these are going to all be sourcing and syncing, either sourcing or syncing sensors on your car, because your car, even though we have an alternator, as soon as it's alternated, as soon as it creates that AC, they right off the bat, they convert it into DC. So everything on your car operates off DC. And we constantly turn things off and on and off and on and off and on, so this is where that would come into play. Your garage lights, that probably operates with a device called a triac, which is a solid state device, either that or a relay. Older lights would probably have a relay. That could be DC. You're right. So if it's got a relay that clicks, then it could be DC.
Gotcha.
So any questions so far? So later on we'll talk about triac, which is basically it's a solid state relay is what it is. It's really cool. And so we can also set up a saturated switch or switch a DC to do what we call a constant current source. So what I'm going to do is I'm going to come over here and put, let's say I come over here and connect this constantly to 5 volts. And let's say this is a 1K ohm resistor. So let's say, to get it right, let's say it's 5.7 volts. So what that does is that's going to put 5 volts right there. So IE would be equal to 5 divided by 1K would be 5 million. Even if nothing's connected to the collector. If I come over here and I put that on there, well, that's not true because here's our current plug. Now let's say I come up here and I put an LED. Two volts at 5 milliamps. Well, and I come up here and I connect this to plus 12 or plus 15. Well, so we're going to assume that your collector, we're going to say IC is approximately equal to IE. Even though we know it's not, we know it's slightly less, but a while ago we looked at it, it was back in so over here we had microamps, over here we had milliamps. So over here we had microamps, over here we might have said, 5 milliamps, and then we would subtract the microamps and that would give us IC. So for all practical purposes, for conversation, we're going to say IC and IE are equal, but they're not. So in a test, if it says IC equals IE, that's going to be false. If we say IC approximately equals to IE, then that would be true. So what would happen is that this guy, we're setting our current with this emitter resistor right here. So this is where that voltage, that's where that voltage based emitter would come into play. So if I come over here and measure between here, it's going to measure approximately 7 tenths of a volt, which would be true. A while ago, if I measured between here and here, but VE VE would be equal to measured from common, so VE would equal to 5 volts. So that's why it's important for you to learn these designators. This guy drops 5 volts. This guy drops 2 volts at 5 milliamps. So what we did is we set the 5 milliamps with this resistor right here. This cannot go up. If it tried to go up, then that would cause this to go up. Well, this is not going to go up, right? You understand that? Because we're going to set it at 5.7 volts. So what that means is this guy here is going to drop 2 volts. This guy here is going to drop 10 volts. That means my voltage emitter to collector, according to Kirchhoff's law, would have to be the sum. So that's going to be equal 15 volts minus 7, which would give us what, 8 volts. So my transistor is going to drop 8 volts. Well, what would happen if I come up here and put another LED? It needs 10 volts at 5 milliamps. Well, I'm setting the current right here. I'm setting the current right here at 5 milliamps with this resistor right here. So what would happen? That would be 4 volts, 4 volts, 5 volts. So that's going to leave 6 volts here. So what's happening is what we're doing, let's say I add another LED. Doesn't make any difference until I run out of voltage, until my three LEDs try to drop more than what's left. So right now, we can get up to 10 volts. We can keep adding these things in series. So we can use these transistors as what we call constant current sources. Now this becomes very important because lead acid batteries, what we do is we put a voltage on a lead acid battery that's greater than what we want to charge it to. And that forces current to flow back through the battery and charge it back up. So lead acid batteries are voltage charged. NiCad batteries and lithium batteries are current charged. So what that means is what it does is it starts off with a high current, and as the battery charges up, then it's going to drop more voltage, but you're going to try to charge that at a constant current rate. So this would be the circuit you would probably use if you were going to design a charger for either NiCad batteries, they're safer than lithium batteries. Lithium batteries like to catch on fire if you get them too hot, if you charge them too hard, right? You understand that? So we had problems with these little hoverboards that kids were buying, and a certain charger did not work right. So what it did, it didn't maintain that constant current. And what happened when they did what? Caught on fire. So I think even on airplanes, they don't allow you to carry. I don't know. Most. Yeah, I need to click on it. So what we can do with a transistor is we can set the current flow with whatever current I need with the emitter resistor. Yeah, but always. Well, no, the problem is, and we'll be okay from here. Let me get back to where I was at. Yeah. So if I came over here and added another one, automatically it's going to say, okay, this guy here is going to drop 2 volts at 5 milliamps. Well, the problem is I only got what up here? The only thing I got up here is plus 15 volts. So I can't have more than 15 volts dropped in my circuit. So as soon as the transistor saturates, so when it goes below 1 volt, then we can't add any more. We can't add any more LEDs. And you see some of this time I've seen this used on car burglar alarms where you put LEDs that flash, and they say you can put up to 5 LEDs and you just hook them in series. Well, how can you do that? Well, they're on a constant current source, right? You understand? So what you do is you come up here and you set the current with your emitter resistor. And if the current tried to go down, that means this voltage right here would try to go down. That means this would try to go above, this would try to drop down. It can. It's going to be locked at 4.57 volts. The transistor would automatically cut on. If this voltage tried to go higher than 5 volts, the transistor would automatically start cutting off, right? You understand that? So we call this a constant current source. Very easy to design. You just choose an emitter resistor and an input voltage over here to get the current that you want. So if I had 12 volts and I wanted 15 milliamps over here, then I would choose a resistor that would drop what? Yeah, it'd drop 11.3 volts at 15 milliamps. And then of course we would choose a resistor. We'd either decide to go up or go down depending on the current demand of the load. LEDs, when we say 15 milliamps, you could put 10 milliamps through it, it just wouldn't glow as bright, right? So you start off with so in my car it's a 12 volt system. Well, actually you wouldn't design it around 12 volts, you'd probably design it around 14. Because that's what your car puts out when it runs. Your alternator puts out about 14 volts DC. So, but 14 volts, 12 volts probably wouldn't make that much difference on an LED because this 15 milliamps we can run them a little higher, we can run them a little lower. Light bulbs, a light bulb's rated, so you got a light bulb at your house that's rated at probably 115 volts. Do you put 115 volts on it? Probably not. So if you put above 115 volts on it, it's going to be a little brighter. If you put less than that, it's going to be a little dimmer, right? You understand? But it doesn't hurt the light. So that's why light bulbs are rated at a voltage. And they rate them at 115 volts, even though NEC says the nominal voltage is 120. So most of your loads, even though they're rated at a certain voltage or power, then those are not precise. Those are not exactly precise. So usually, whichever one you design around, either 12 volts on your car or 115 volts or 14 volts, you're okay. Somebody fixing to say something? I heard somebody unmute their microphone. So this is a constant current source. So I could build a charger I could look at the lithium battery, look at the charging specs to see what current's required to charge that thing, and then I could build my own charger. NiCad batteries, if you still use those. The problem with NiCad batteries is that they get a memory, by the way. So if you got NiCad batteries, guys, you don't need to leave them things charged all the time. Huh? NiCad. That was the first chargeable battery they came out with. And there's still a lot of devices. So a NiCad battery gets a memory. So that means the more you charge it, the faster it runs down. So a NiCad battery, you need to charge it up, run it till you get a low voltage warning, charge it back up, and then that's okay. Lithium batteries, so most batteries have a discharge curve like this. Lithium batteries has a discharge curve like this. I don't know if y'all have ever been using like a handrail, and all of a sudden it'll be running and then just stop. Because lithium batteries don't give you a warning. So the motor don't start running slower on a lithium battery. It just dies. NiCads has a discharge rate of about the same as a lead acid battery. So that means if you have a lithium battery on your car, instead of your starter turning all over slow, it just wouldn't turn over at all. So lithium batteries, you got to be careful on those. Lithium batteries are unforgiving, which means they're a lot more forgiving than the NiCad batteries. So you can leave those on a charger pretty much well all the time. They're using lithium batteries. As far as I know, lead acid, they're using a lot of batteries. And lead acid, when lead acid charges, when a lead acid battery is charging, it creates hydrogen. Yeah, y'all know hydrogen, right? What's the problem with hydrogen? It burns really easy. So that's why they stopped using hydrogen in blends. So what was the famous bib that caught on fire? Callaway. Yes, but it's water itself. It's not the water. It's the hydrogen in the water. It's pure hydrogen is what gives you problems. In a chemistry class, that's one of the things we did is we had an electrolysis machine in sulfuric acid, and we put regular water in there, and when you excited it would dissipate and create oxygen and hydrogen, and then we'd burn the hydrogen off. So hydrogen is highly flammable. That's what they was using in the shuttle that blew up. They were using hydrogen in there. So it's very, very volatile. What was the name of the Zeppelin that caught on fire? Anyway. So guys, so what we're doing is next thing we'll look at is voltage divided by. So we'll actually look at the different ways we can actually bias over single voltage. So the problem with this arrangement right here is that this requires two supplies. And we can't do this on our trainer because we either got to have two positives or two negatives. So the problem with our trainer is our power supplies are like this. Our variable power supply. And then this right here is our common. And of course this right here would be the plus supply. And this right here would be the minus supply. So we can't wire this circuit right here with our trainer's power supplies. We can use one of them. So notice this. On this one, we would have to have the minuses connected together. Well, our trainer power supplies, we can't do that. So when y'all wire up this circuit right here, you can use one of the trainer's power supplies. So we might use this one for this one, and then we would have to use another power supply to get this one. And that's where those other power supplies that I'll show you would have to come in. We could use two trainers because the trainers, this is not a ground. This is a common, even though they call it ground. And using the term ground is okay if you understand the difference between a common and a ground. A ground means it's connected to earth ground. A common means it's just a common conductor used by the circuit. So technically, a common should use this symbol right here. It's kind of like a diode, but it's not covered. It's not colored in. This is the symbol that actually is designated for a ground. This is the most unused symbol, or the most misused symbol in the electrical and electronic branch. And everybody wants to call the common conductor, they want to call it ground. It's okay with me. I'll probably correct you in my class, but when you get out there, we was doing a video on on electrical safety, and they said that the ground is the wire that holds zero potential. And then later on, they started talking about the ground on a power receptacle. And if you don't understand the difference, the ground on a power receptacle is a reference to earth ground. So they were using the same term, but they did not define the difference between what they call one ground and what they call another ground. So you got to be real careful with that. So our trainer, the metal that all the components mount on, that is grounded, but none of your power supplies are grounded. And I've seen some of y'all try to use that terminal. So the only thing that ground is on there, that is a common, is for the power supplies that are in the trainer. On your circuit, your common is your common. So on all your power supply circuits, you are creating your own power supplies. You do not connect it to that black terminal that's on the trainer. You establish the common for the circuit. Don't. And I probably came over there and pulled it off some of y'all's saying this is not a ground, it's not your common. So what does the symbol represent? Well, the symbol's supposed to mean that conductor is grounded, but it's representing a conductor. So normally on these, we wouldn't draw this thing like this. Normally in electronics, we would not draw the common. So what we would do is we would come over here and look, you'll probably never see, we would get rid of this altogether, and we'd come down here and we would use the same symbol on all three of these. So that symbol is representing a conductor that's there. That means on that trainer, all those power supplies are referenced to that black terminal. So what that symbol does, it represents a wire. And I've seen this on some of y'all where you'll have a resistor hooked up to a trainer, and you'll come over here, have your resistor hooked up over here, and over here you'll have something applied here, and you just leave that one hanging out in the air. And then they'll say, is this right? I said, no, what's that resistor connected to? You know, and knowing the difference between series and parallel. So I've seen this several times where you got the output of your power supply, and you're supposed to put a capacitor in parallel with the resistor. And I've seen this more than once, guys, where you come in here, you put your capacitor over here, and then you put your resistor over there. This is not in parallel, this is in series with that resistor. I've seen this twice already in labs in this class right here. So parallel means they're two leads connect together, right? You understand that? So we'll see that. So that's about all the time we have time for today, guys. And what we'll do on Thursday is we'll come on campus and we'll finish up this lecture, and then we'll let y'all go in and work on your labs. So this is the only slide we have left. So we got 1, 2, 3, 4, 5, 6, 7, 8. These are the same, by the way. I just noticed that. 8, 9, and we'll look at these. And I'll probably hook this circuit up so we can actually see it operate. We'll look at this different type of bias. So notice this has only got one power supply. One power supply. And we'll look at the different biasing, and this will be the only one that is really looking at. It's called voltage divider bias. And what laws are we going to use here? We're going to use Watt's law, or we're going to use Ohm's law, and we're going to use Kirchhoff's law to calculate this circuit. All right, guys, y'all got any questions?
Nope.
So hold on, let me see who's still here. So let me